So, in the previous lecture we discussed how to get the path of this orbit if a particle is there under a central force, inverse square central attractive force, and these are the steps. In fact, you can start with total energy, and angular momentum are known from the initial conditions. You write m r dot square from here, and from there r dot, and that becomes function of r only, and therefore, in principle you can bring this side, it is a function of r, and that can be integrated with respect to r, and this side is t. So, you get t as a function of r, and then algebraically you manipulate and write r as a function of t. And once r as a function of t is obtained, then you can come to this equation, and from here you can write theta dot, which is L by m r square. Now, this whole thing is a function of time, and therefore, r is a function of time, and therefore, you can integrate this out and write theta as a function of time, and then you can eliminate time from this equation and this equation. That gives you relation between r and theta, and that is the equation of the path in plane polar coordinates. So, you know what is the orbit, and if you work out the conditions that we have already discussed with energy diagram qualitatively, that if this u is greater than 0, it turns out to be a hyperbola. If this u is equal to 0, it turns out to be a parabola. If this u is less than 0, then it turns out to be an ellipse. We will be more interested in this elliptical orbits, where the initial conditions are such that the total energy is negative. The potential energy minus k by r has a much larger magnitude or larger magnitude than the kinetic energy half m v square. So, the total energy is negative, and then the orbit is ellipse, and the equation of that orbit, if you work out, that will be r equal to some constant r naught divided by 1 minus e cos theta, where r naught is L square by m k, and this small e is square root of 1 plus 2 times total energy times L square and divided by m k square. Now, this quantity is known as eccentricity of the ellipse. This quantity here is the eccentricity. It gives you equation of an ellipse if this E is between 0 and 1. Okay, so this is the equation. If you want to see how this can be an ellipse, you can take some values and convince yourself that it looks, at least it looks like ellipse, and that will also give you some feeling of this E here. So, let us take this example. Let us say E is 0.1. What happens? R is equal to R naught divided by 1 minus 0.1 times cos theta. Suppose this distance is r naught, this distance is r naught, and I have put this point, it will be on the ellipse, because here theta is 90 degree, and if you put theta is equal to 90 degrees, this is 0 and r is equal to r naught. So, you will have a point here on the ellipse, and what happens if theta is 0 degree, then cos theta is 1. It is 1 minus 0.1. So, 0.9 r naught divided by 0.9, little more than r naught, little more than r naught. So, you have a point somewhere here, little more than r naught. If theta is pi, cos theta is minus 1, then it is 1.1, r naught divided by 1.1, a little less than r naught. So, a little less than r naught somewhere, let us say here. So, it is of this type, it is of this type. So, you have an ellipse you can draw it to the scale, you can use an Excel file and put the values of theta, get the values of r, and then you can make tables and you can plot and you can see how it looks like. On the other side, if you take E is equal to say 0.9, what happens? R is equal to r naught divided by 1 minus 0.9 times cos theta. So, now if you have the same r naught here, because at theta equal to 90 degrees this will be 0 and r will be r naught. So, this point remains the same, but the point on the x axis theta equal to 0. If theta is 0, cos theta is 1, 1 minus 0.9 is 0.1 only. So, this is r naught divided by 0.1, 10 times r naught. 10 times r naught. So, you have a point at a very large distance here, and on the other side if theta is pi, this will be 1 plus 0.9, very close to r naught by 2. So, another point is here. So, now you can see, you can write this as so, as the eccentricity increases, this ellipse become more and more elliptical. If it is close to 0, it is close to circle, and if it is close to 1, then it is a very elongated cigar type ellipse. What happens if E is equal to 0? If E is equal to 0, if E is equal to 0, where? Here, if this E is equal to 0, r is equal to r naught, r is equal to r naught for all theta. So, that is a perfect circle, right. And if E is equal to 1, if this is 1, then it is 1 minus cos theta, and at somewhere it will blow, or more than 1, somewhere it will blow, go to infinity. So, if E is equal to 1, then it is a parabola. If E is greater than 1, then it is a hyperbola. If E is less than 1, between 0 and 1, then you have ellipse. So, that is how. And you can also get this idea of how elongated it is from this r minimum and r maximum. So, what is r minimum here? R minimum is r naught divided by 1 plus E. R naught divided by 1 plus E, and R maximum is R naught divided by 1 minus E. Okay. So, this is your maximum and this is the minimum, and here this is the relation. If you see the ratio R max by R min, that is 1 plus E divided by 1 minus E. That also will give you a fairly good idea that how much is this. And then eccentricity, you also have a relation that if I take the center of the ellipse, then this is called semi major axis and this is called semi minor axis. Okay. From the center of this minimum point and maximum point, theta equal to 0 and theta equal to pi, from the center if you draw a perpendicular line, then half of this whole distance, this is known as semi major axis, this point to this point is known as major axis, and this perpendicular, this point to this point is known as minor axis, and this is semi minor axis. And the relation between these two is B is equal to A square root 1 minus E square. So, B by A is equal to, or A by B, okay, B by A is equal to square root 1 minus E square, and A by B will be reverse of this, 1 divided by square root of 1 minus E square. So, from here you can also see, if E is close to 1, if E is close to 1, then this quantity is very small and this quantity is very large. The major axis is much larger than the minor axis, and that is what I mean by that elongated ellipse. Whereas, if this E is close to 0 and this whole thing is close to 1, then A is close to 1, A is close to B, and then the minor axis and major axis are roughly equal, and that is nearly a circular orbit. So, this eccentricity decides the shape of the ellipse that it is there, and physically the eccentricity depends on these quantities: total energy, the angular momentum, which are constants, and then of course mass of the particle and force. This constant k is coming from force, remember it is k by r square, force is k by r square, that k. So, these things will finally decide what is the energy, and remember this u is negative, remember this u is negative. So, this E is less than 1, and therefore, it is an ellipse. Okay, let me also write how much is that major axis, okay, and you will see a very interesting result. So, if you write that major axis 2a, that is r min and plus r max, this is the major axis, and this is r naught divided by 1 minus E plus r naught divided by 1 plus E, and that is r naught. Here you have 1 minus E square, and then you have sum of these two, which is 2. So, 2 times r naught divided by 1 minus E square. How much is this? This is 2 times r naught. R naught is where is r naught? R naught is L square by m k. So, this is 2 times L square by m k, and then 1 minus E square. What is 1 minus E square? E square is equal to 1 plus 2 u L square divided by m k square. So, 1 minus E square is equal to minus 2 u L square by m k square. So, right here 1 minus E square is equal to 2 u L square and then m k square. How much is this? L cancels out, not u, L cancels out, 2 cancels out, m cancels out, and this is just 1 minus E square, minus of this, right. So, minus of this. So, it is minus here, and then k here, 1 k cancels out, and divided by u here. This is it. So, u is equal to minus k divided by 2a. The total energy decides the major axis, or if you know the major axis, you know the total energy. It does not depend anything on anything else. So, this is one beautiful result that one can remember. Okay. Another thing what you can do is to calculate the time period. If the particle is going on this ellipse, how much is the time taken? And for that you already know that the rate of area swept by this radius vector. So, at some instant the particle is here and then the particle reaches here. So, this is the area, this is that area covered, and dA dt is constant. So, this area is increasing at a constant rate, and the total area of ellipse is known. dA dt is what? L by 2 m, right, m r square theta dot m r square theta dot, this is L, and this is 2 times m times half r square and then d theta dt. Okay. And this is that area dA, this is that dA. So, L is equal to 2 m and dA dt, and therefore, dA dt is L by 2 m, dA dt is L by 2 m, correct. The total area of this whole ellipse is, which the radius vector has to sweep in one full revolution, that is pi a b. So, the time period will be pi a b, this is the total area, and divided by this dA dt, which is L by 2 m, divided by dA dt. This is the area swept per unit time, and total area to be swept in one revolution is this, and therefore, when you divide you get the time. So, this is pi into a, and b is a square root 1 minus e square, and divided by dA dt is L by 2 m. So, L here and 2 m here. So, it is 2 m pi a square by L, 2 m pi a square by L, square root of 1 minus e square. 1 minus e square we had written, this is 1 minus e square, this is divided by m k square. Once again we can do it from here, 1 minus e square will be equal to minus 2 u L square by m k square, and square root of that, square root of this. So, it is square root of minus 2 u L square and by m k square. What cancels? This L cancels with L square. Okay, then all right. So, this is it. So, this is equal to 2 m pi a square divided by this m I can take inside the square root. So, this will be square root of m here, right, m here and square root of m here. When you cancel, square root of m goes in the numerator, that we are writing here. 2 pi a square we have written, and therefore, we only have to write the rest of it. So, minus 2 times, okay, let us write 2 times minus u. What is minus u? Minus u is k by 2a, minus u is k by 2a. So, this is 2 and minus u is k by 2a. So, it is k by 2a, right, k by 2a, minus u is k by 2a. We have written this, divided by k square. So, k I can write here. All right. So, yeah, there is a root k here and k here. Okay. So, let me write k square and then I will cancel it. This is equal to 2 pi a square and then square root m by k, right, m here and k here, 2 cancels, a is in the denominator. So, divided by square root of a. So, this is 2 pi square root m by k and then a to the power 3 by 2, or t square, capital T square is 4 pi square and then m by k and then a to the power 3. So, if you have a gravitational attractive inverse square law, sun and different planets. What is this k? In that case, k is capital G m m. The force is k by r square and the force is g m m by r square. So, k is g m m. What is m by k? M by k is 1 by capital G m. Small m divided by k is equal to, small m divided by k is equal to 1 by capital G m. So, this is 4 pi square divided by capital G capital M a power 3 by 2. The mass of the particle has gone. If this is the case, if this k is proportional to the mass of the particle, which is the case in the gravitational attraction at least. If k is proportional to m, m by k is independent of the mass of the particle. So, in the sun planet system, you consider any planet, Earth, Mars, Jupiter, whatever, any planet, no reference there, and it is only the semi major axis which is deciding this time period. Square of the time period is proportional to the cube of the semi major axis. Okay, square of the time period is proportional to cube of the semi major axis. This is Kepler's second law. Kepler described all these laws on the basis of observation of positions of planets at different times round the year. These observations were taken by Tycho Brahe, and Kepler analyzed those data, and from there he formulated these rules. The first law: all planets go in elliptical orbits with sun at one of the foci, and that we understand now using all that algebra. We know that yes, this is the equation, this is the equation of the ellipse, and therefore, the particle or the planet has to go on the ellipse and the sun will be at the focus. Then the second law is here. Oh, this is the third law in fact. The second law, popularly known as second law, is that radius vector sweeps equal area in equal time. So, that we have already seen, that is valid for any central force, not only inverse square attractive. Okay. So, Kepler observed it very rightly from the data that it sweeps equal area in equal time, and then the third law that square of the time period is cube of this semi major axis. So, that also comes from this analysis.